Hello and welcome. Machine learning is complicated and at the same time more accessible to the average person than ever before. I'm here today to show you that no matter who you are, you can do it. And we'll get there using an example that's not boring, the NFL draft. In my last video, I jumped to the results quickly and skipped over a lot of details. For this video, I want to slow it down a bit. We'll focus on three phases: the preparation, the execution, and the results. Welcome to Data Rift. I started this channel because I'm eager to dive into applications like this, share what I've learned, and grow with you. With that out of the way, let's dive in. We're going to demo this model with Google Colab. It's a great tool and lets you write and execute Python in a web browser. It also has a really cool Pro subscription. It features a large language model that helps you write the code for your project. I highly recommend this feature, especially if you're just starting to learn to code. And even if you are experienced, it can help you quickly get used to a new library like Tensorflow, which will be featured in this video. In case you haven't heard of it before, Tensorflow powers deep neural networks with high-level code. It was developed by the Google Brain team in 2015. It's used by Twitter to rank tweets, by Uber to optimize driver resources, by Spotify to give you song recommendations, and Airbnb to detect and correct inaccuracies in listing photos. But by far the coolest part of TensorFlow is how it makes complex machine learning accessible to both experienced developers and people who might just be learning to code for the first time. At least 75% of your total time on a project like this will be in the preparation. Acquiring and organizing a good data set is the foundation of a good model like this. You can't rush it. Shortcuts in this phase will doom the project. Before we write any code, ChatGPT highlighted a few fundamental concepts that are critical if you want to build a model that's of any use. In the first three steps, it emphasizes the importance of data collection and preparation, defining the prediction task, and the model design and training. All of these things are very related. Before you even start collecting and organizing your data, you have to start with the end in mind. In this example, I really envisioned a regression model, so I organized and pre-processed my data with that end in mind. With that kind of model, you want numbers, so classification data like position and the school that person is from, they really don't directly help you out. That doesn't mean you can't use that valuable data. It just means you might need to transform it into something different, like how valued that player's position is. How likely are they going to go at the front of the draft? How historically valued are players from whatever school? And finally, what's the landscape of the needs of the teams in the first round? We can quantify all of these things with some creative formulas. This is where you might run into some analysis paralysis. Keep in mind that even if you were a professional analyst for one of these teams, we're still talking about an extremely complex task. So I encourage you to trust your gut and just throw something out there and see how it does. If you get to the end and you don't like your results, this is an area you can come back to and fine-tune. For these models, you really want as much data as you can possibly get to reliably train them. Two things that made this already difficult task even more challenging are: 1, I didn't quickly find an abundance of useful data sources. 2, when you find them, the different sources need to be consistent with each other. A great example of this is player grades. It would be really cool if you had player grades from many different sources all compiled into your dataset. But I found it really hard to find consistent sources for these player grades, especially the further you go back with historical data. So I wound up just landing on one data source for player grades, Pro Football Focus, because they consistently have numbers from year to year. Apart from PFF, all the other data I used in this project came from NFLMockDraftDatabase.com. Specifically, I pulled their historical data on team needs, draft order, draft results, and consensus big boards over the years. Again, a lot of this data has to be pre-processed to fit my regression model design. Now, we're finally ready for our model. The template for this code is on TensorFlow's website. It's in an example that I will link in the description of this video. I repurposed the code in that example with relatively minor edits to fit my example. In this first section, I'm just putting together all the project dependencies in one place. Next, we're importing both our training and testing data sources. For this example, we're training with data from 2018 through 2022 to try to predict the 2023 results. From here, we do a little more organization, we normalize the data, and we're ready to plug it into our model. Remember, I set up the data with regression models in mind, and those will be the first two I will test. We'll then test with two deep neural network models. For the first regression model, I'm just going to look at one variable. I want to know how the model predicts draft order based on the consensus big board data from one source on NFLmockdraftdatabase.com. For model compilation, there's a couple things to note here that are crucial for getting optimal performance, particularly the Atom Optimizer. This is a method that's being used to tune the neural network to reduce loss and improve the model, the learning rate. For big models, this might be one of the variables you adjust to balance for time and performance. If it's too small, it might train forever, but if it's too big, your model might not be effective. Here, we're showing our training losses and validation losses. As the model completes each cycle through the dataset, this is known as epoch. It's telling us how well a model is learning and generalizing the data. With that comes concepts of overfitting and underfitting. For overfitting, you'd see diverging losses with one increasing and the other one decreasing. There's no evidence to suggest that's going on here. Now, underfitting is a different story. Here, you can see both losses are still declining and not really plateauing. So honestly, this is probably telling us there's more room to keep training. Also, the gap between the losses is telling us there's room for improvement with our model. But hey, if I had this right, I wouldn't be here on YouTube. I'll be trying to figure out the best use of my blank check from Amy Adams Strunk. Here, you can see the results of the one variable regression model. There's some things that jump out here, but we're going to take a brief look at the other models and come back to this graph. Quickly now, the multivariable regression model uses more variables as the name implies. We're still seeing the same kind of results seen in the previous regression model. It gets more interesting with the deep neural network models. This is where I'm setting up the layers for the network. This is an example of a simple design, but there's a lot that can be done here. In general, it's better to start simple and increase complexity as needed. Taking a look at the results, we see a sharp decrease in both losses, which means it went from a state of high error to a more optimal set of parameters very quickly. However, the complexity of this problem can't be understated, as we see it levels off and never gets better. Generally, this could indicate that we need more data and there's more room to optimize our model's architecture. And we see similar results from the multivariable deep neural network. An interesting thing that stood out to me was I designed this all along to be a regression model, but the deep neural network got better results. This tells me I was probably dumb to try to fit this problem into a regression model with its limitations. After all, it doesn't take a genius to figure out this is highly nonlinear data. Year after year, we see locked-in top 5 picks plummet in drafts, and at the same time, see GMs fight for one or two guys that are much lower on most boards. We've already talked about some room for improvement on the model side, but if we come back up here to our predictions graph, you can see how I handled certain sets of data. Up here, you can see players on the consensus player boards that went undrafted. I gave players like these a draft value of 500 in the data. Likewise, you can see guys that are beyond the consensus top 100 that got drafted. These players were given a consensus position of 150. I did both of those things with intention that I know what I'm looking at when I see them, but in hindsight, they're probably doing more harm than good. How these situations are handled are another room for improvement. At this point, I better appreciate the complexity of this problem, and I'm good with the result. So now we've covered the example, and I really hope that you found some value in this time and feel more confident that you really can do this. That said, all that's left is to show you the results. Here's how it predicted the 2023 draft. If this was helpful, please like and subscribe and let me hear from you. If you want to see how another model like this one did in predicting last year's March Madness tournament and who it likes this year in 2024, be sure to check out my recommended video. Thank you so much, and I'll see you in the next one.